Okay, so now we have some ideas about sampling techniques. Okay, we will only focus on random samples, and starting from now, we will talk about some properties regarding the distributions of sample mean. Okay, sample mean is obviously a statistic that you may calculate from a sample. We will tell you about what's the distribution of it and what's the distribution when it comes from a normal population or a non-normal population. Okay, let's start. So let me first help you review what is a sample mean. So suppose I have a population and I collect a sample as n numbers. Okay, so they are x1, x2, x3, blah 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 up to xn. The sample mean is simply defined as the arithmetic average of those n numbers. Okay, so that's the definition of sample mean. We will typically hold an assumption on the sample mean is that for different two numbers or two numbers in the sample, we will say they are independent. Here, independent means whether you draw this number does not affect whether you draw the other number. So that's something we need to have when we talk about the properties of sample mean. Basically, if you are running a random sampling, then you have this property because you don't know whether you will get this number or that number. But if you are doing, for example, those non-random sampling techniques, then you don't have this property, right? For example, if you decide who to ask, then you cannot say whether you ask this guy does not affect whether you ask that guy. So in that case, we don't have this property. We will also discuss when do we really have this property and what will happen if we do not have it. But anyway, let's assume we have this property at this moment. So let me start my introduction as follows. First, let's think about a population which has a mean and a variance, mu and a sigma square. Okay? My population here is a set of numbers or a set of multiple numbers. Like I have 1,000 students graduated from the IM department. That's a population. I have all the voters in Taiwan. That's a population. Okay? Each population must have a mean and a variance. The key is that these two numbers are fixed. Okay? On the other hand, the sample mean is actually random. Today you draw a sample. Tomorrow you draw another sample. These two samples will somewhat be different. Okay? Typically. So, as a random variable, x bar has its expected value and its variance. Okay? Sometimes we will use mu x bar and sigma square x bar to denote these two numbers, the mean of sample mean and the variance of sample mean. These two numbers are fixed. Okay? These two numbers are fixed because it's an expectation and variance of a random variable. The thing here is that we know these are two fixed numbers, but we don't know what are them. So if there is a formula to calculate these two numbers, it would be very good because we need to know the distribution of a sample mean, right? So we do have a formula, but before we try to give you that formula, let's do an experiment first. So again, let's go back to the candy problem. Suppose I produce 1,000 bags of candies, and that 1,000 bags serve as the population in this case. Okay, for each bag there is a weight. Suppose my production process is that the mean is at 2, but the standard deviation is so high, it's 0.2. Okay, so That means if this is my normal curve, okay, the mean is 2 and the standard deviation is 0.2. Then what I will have is that for 1.8 and 2.2, for the standard set by my mom, I will only have the range within one sigma to satisfy the criteria. So the probability is around 68%. Okay, so my defective rate is 32% in this case. Suppose my mom wants to test whether I am doing a good job or not. And my mom says, okay, I'm going to sample 4 bags randomly among the 1,000 bags. And then I will calculate the sample mean. If I see the sample mean outside the range 1.8 to 2.2, I'm going to punish you. My mom said that to me. Okay, so then I have some natural questions. First, what is the mean of my sample mean? Okay, the expected value of my sample mean. What is the standard deviation of my sample mean? These are some numbers we want to know, so that we may really describe what's the distribution of my sample mean. Okay, if I know what's the distribution of my sample mean, then for example I may calculate what's the probability for the sample mean to be above 2, or what I really care about is what's the probability for me to be punished. Okay, let's try to do this. So I have a way to mathematically calculate those numbers, but now let's do an experiment first. So I need to first generate a population. Okay, so I use this rnorm function to generate 1,000 numbers from a normal distribution with mean 2 and standard deviation 0.2. Okay, so if that can be done, then X would be my population, and then I will try to sample 4 numbers from my population. In this case, I do sampling without replacement, right? That's something I should do. And then I calculate their mean value. This is going to give me the sample mean. I should then store my sample mean to some variable. Let's call it a mu x bar, something like that. This is my sample mean. Okay, and the key here is that I need to do it for 5,000 times or even more. This is because I want to calculate the mean value, the standard deviation for my sample mean. Okay, if I only collect one number, I cannot say that number is just the mean of my sample mean, right? Because sample mean is random. So today you get a sample mean, that's a number. Tomorrow you get another sample mean, that's another number. So if you really want to know what's the expected value of your sample mean, you need to do a lot of experiments and then average them, or calculate their standard deviation, or draw a histogram for you to get an understanding of that sample mean. So if I want to do that, I am going to write a code like this. Okay, looks very long, but actually it's simple. I set the number of trials to be 5,000, and then I use this function to get my population, right? I first create a vector with a lot of 0. That's going to store my outcome of sample means. And then I do this repeatedly for 5,000 times to random sample, calculate their means, and store them in this vector. Then I can answer the 5 questions I just asked. For that 5,000 numbers, I calculate their mean. That's going to be an estimation about the expected value of the sample mean. The expected number is there. It's a fixed number. We just don't know how to calculate it. with this experiment, we will get a number that should somewhat be close to the true sample mean. We can calculate the standard deviation. We can draw a histogram to get an idea about the distribution. We can calculate the probability for my sample mean to be greater than 2. How? Around those 5,000 numbers, around those 5,000 sample means, I ask which of them is greater than 2. Okay? I'm going to get some indexes that so that for this vector, that particular element is greater than 2. And then I ask how many do we have. That number divided by the total number is an estimation about that probability. And then if I want, I may also calculate the probability for my mu x bar to be less than 1.8 or greater than 2.2. That the sum of those two probabilities will be my probability for being punished. And now the outcome is here. I run that experiment once, and the mean of my sample mean is 1.99 blah blah blah. The standard deviation is 0.100 blah blah blah. The distribution, okay, is here. Is the outcome of the hist function. I would say it's somewhat like a normal distribution, right? Looks like a normal distribution. At least you know, looks somewhat symmetric, somewhat like a bell shape. Okay, it's not a uniform distribution. It's not skewed to the right. It's not skewed to the left. It looks like a normal distribution. The probability for the sample to be above, for the sample mean to be above 2, in my experiment, is around 47%. And the probability for me to be punished is around 5%. Okay? So collecting these ideas, I somehow get an intuition or get a conjecture about the distribution of my sample mean. It looks like normal. Its mean looks like around 2. Its standard deviation looks like 0.1. Right? This is just a conjecture based on my experiments. And I may also calculate some more things. If my sample mean is really distributed like this, then I know, okay, this will be a normal distribution. The mean will be at 2. And now, for my mom, she says the criteria 1.8 and 2.2, right? But now, because my standard deviation of my sample mean is just 0.1, so I know the probability for me to get a number within this region is the probability of within 2 standard deviation, and that's 95%. Okay? So that confirms the outcome here. The punishment rate is around 5%. And also because standard deviation is symmetric, so the probability above 2 should be exactly 50%. 47 does not really look similar to 50%, but it's also not a very large deviation. And we know deviation should exist because this is just an experiment, right? But anyway, through this experiment, we now get an idea. It's possible that we really have a distribution of my sample mean. Okay? Now we want to ask whether this is always true or not. So in the next video, we do the derivations. Thank you.